We are going to dig in a little bit more into precision and accuracy as well as error. A measurement that's said to be precise is if it yields very similar results when repeated in the same manner. A measurement is considered accurate if it yields a result that is very close or true to the accepted value. And what is the accepted value? Well, let's say that you're playing darts. If you're playing darts, the accepted value is hitting the bullseye. That would be accuracy. So let's look at letter A. The arrows are close to both the bullseye, there's 3 of them, and they're close together. So if they're close together, you're precise. Accuracy is if you're hitting the bullseye. So this would be both accurate and precise. Let's look at letter B. Notice that these 3 little dots, they are close to one another. We can say that they're precise, but it's not hitting the bullseye. Nobody's right there. So they are not accurate. Let's look at C. These arrows are neither on target, they're not on the bullseye, so they are not accurate. And I would even say that they are not very close together. I guess it depends on who's saying that they're not close together, but they're not very close together. So they are neither accurate or precise. Let's look at an example where we're measuring out some cough syrup. Medicine is delivered by a 10-ounce or 296 milliliter dispenser. So let's say we're using dispenser number 1. Again, accuracy would be hitting 296 milliliters. This person got 283.3, 284.1, 283.9, 284, 284.1. Notice that these are all very close numbers together. 284.1, 284.0, that's just a tenth off. Between here and here is just a tenth. These two are the same, 284.1. They're very close together. So they are precise in dispensing that medicine. But is it 296? No, not accurate. Let's look at dispenser number 2. 298, 294, 296, 297, 293. Now, it's more accurate. It's definitely closer to the 296. I would not say that it is fully accurate. It is more accurate, but look at this. It's less precise. We have some values here at 298, but there's some values here at 293. I would say that those values are not precise, not close together, so definitely less precise. And then let's look at dispenser number 3. 296.1, so that's just a tenth off from the 296. 295.9, again just a tenth off. 296.1, a tenth off. And those two are the exact same. So are these two the exact same? And this is spot on. Dispenser 3 is both accurate and precise. Why don't you pause the video here and see how you would rate these different archeries. Let's look at Archer W. We have our 4 throws here. They're not very close together. Now they are kind of close to the bullseye being right there. So I would say that it is more accurate, and I would say it's somewhat precise. So I would say more accurate than others and more precise than others. Let's look at X. So we're just kind of comparing. Now look at these 4. They are very close to one another. I would say that this is precise, but it is not accurate. Why? These are all over the place. They are not precise, not accurate. Also for Z, not precise, not accurate. Those dots are not anywhere near each other to be precise, and they're not anywhere near the bullseye. Now we do have one, I guess, that's near bullseye. We could say that we have one of our throws is near accuracy, but as a whole, no. Let's look at experimental error. If you measure a quantity in the lab, you might be required to report the error in the result, which is the difference between your result and the accepted value. So to find the error, you take the experimentally determined value and you subtract the accepted value. So this is yours, your experimentally determined value, minus the accepted value. Or you can find the percent error. To find that, you take the error of measurement divided by the accepted value and times it by 100%. Let's look at an example. Suppose a coin has an accepted diameter of 28.054 millimeters. So we have 2 students and they measure the diameter. Student A makes 4 measurements of the diameter of the coin using a precision tool called a micrometer. Student B uses the same coin using just a simple plastic ruler, and then they report the results. So they have 4 measurements. Student A, 28.246, 28.244, 28.246, 28.248. Student B says 27.9, 28, 27.8, 28.1. What are we going to do with this? Well, we said back here that we needed to find our experimentally determined values. Well, if we have a bunch of values, we're going to need to find the average for that data set. And to find the average, we're going to add up all of those values and divide it by 4. So the average for student A found that it was 28.246 millimeters. And the average for student B was 28.0 millimeters. So let's find the percent error for each student. We're going to take what the student got, so for A, minus the accepted value, the accurate value, divided by, again, the accepted value, which we were told is 28.054, then times it by 100. So we got 0.684%. We're going to do the same thing with student B. Instead of the 28.246 value here, we're going to sub in 28.0 minus 28.054 and divide it by 28.054, and we would get negative 0.4%. Which one is closer? Now, assuming that this negative, we can assume that that's off because we're only 0.4% off in the smaller direction is what that's implying, as opposed to this student is 0.684% off. So student B's average is actually more accurate because it is closer to the accepted value, so it has a smaller percent error. Why don't you try? Let's say a student checks the accuracy of 2 standard top-loading balances by testing them with a standard 5.000 gram mass. That is our point of accuracy. Here's our results. Balance 1, balance 2. Calculate the average values for balance 1 and balance 2 and calculate the percent error. Pause the video and tell me which balance is more accurate. Hopefully you found that the balance for number 1 was 5.02 grams and the average value for balance 2 was 4.97 grams. So to find the percent error, we took balance 1 minus what we got before we averaged it, minus the 5.000 grams and divided it by our accurate value, so we got 0.35%. For balance 2, we took our before we've rounded value minus the 5 grams divided by the 5 grams times by 100, we got 0.65%. So which one is closer to 0? The 0.35%. So balance number 1 is slightly more accurate. We are moving on to talk about scientific notation and significant figures. Let's start with scientific notation. Numbers in science are often really large or really small, and so to avoid confusion, we use scientific notation. It utilizes significant digits in a measurement followed by a power of 10. Now, the significant digits are expressed as a number between 1 and 10. For example, if I had 979 and I wanted to write this in scientific notation, to write it as a number between 1 and 10, I would need to put my decimal point right there. 9.79 is between 1 and 10. Not, if I put it right there, that would be 97.9. That's way bigger than 10. I don't want to put it right here. 0.979 is less than 1. So I'm going to erase this. So 9.79. And I'm going to say times 10 raised to the power of how many spots do I need to move my decimal point to get it back to the large number that it was, 979. Technically, the decimal point would be right there. Well, when I moved it to right here, that means I need to move it 2 spots to the right. So it'd be times 10 to the second number. So this n, this integer, is a positive integer. If that integer is greater than 0, then our fixed decimal form is big. It's a big number. This is 979, or let's say I said 9,240. That's a big number. So to make this a number between 1 and 10, I would make this 9.24. I'm not going to include that 0, and you're going to see why in just a little bit. Times 10 raised to the, so plop my decimal there, 1, 2, 3 spots. So if I have a number here that is a positive number, it's because it's a big number. If it's a smaller number than 0, a negative number, then it's a small number. For example, what if I had 0.0000391? Well, to make this a number between 1 and 10, I would plop that decimal point right here between the 3 and the 9, and I would say 3.91 times 10 raised to the, now I need to go to the left to get back to my original decimal. How many spots left? I need to go 1, 2, 3, 4, 5 spots left. So I would say -5. That negative just implies that I'm moving to the left to get back. So that tells me that it's a decimal, not a big number. For example, let's say that I have, whoa, this many helium atoms in 1 liter of helium gas. Express this number in scientific notation. I need to plop my decimal point in a spot to give me a number between 1 and 10. So I would make that 2.68 is where I would put that decimal point. And now I need to get it back to where my original decimal point is. My original decimal point is all the way down here to the right. It's a big whole number. How many spots would that be? Hopefully you counted 22 spots. So 2.68 times 10 to the 22nd atoms. What if I told you that the typical length of a carbon and oxygen atom is this many meters? What is the length expressed in scientific notation? Well, if I need to plop that decimal point in between some numbers to make a number between 1 and 10, 116, I'm not going to put it there because that would be 0.116. That's not right. That's not a number between 1 and 10. It would need to be here, 1.16. And I need to move left. How many spots to get back to here? Should be 7 spots left. I would like for you to pause this, and I would like for you to express each of these following ordinary numbers in scientific notation. So pause the video here, and I will put up the answers in a minute. Hopefully you got these right answers. If not, go back and look at them. Here's some more practice. Express each of these numbers that are in scientific notation in ordinary numbers. So you're going to be writing out some big numbers here. Check your work and see if you got it correctly. Now let's say that you're doing some math on your scientific calculator and your calculator spits out an answer that says 7.45 e negative 17. This e is simply telling us that we have 7.45 times 10 raised to the negative 17th power. That's what that is implying. So just be careful when you're using your calculator. I can always help you. Now we've been talking about significant figures, and I've kind of been pushing it off, but here we go. Significant figures are numbers that are always significant, and here are the ones that are always significant. Any non-zero numbers. That means anytime you see a 1, 2, 3, 4, 5, 6, 7, 8, or 9, any non-zero number is always significant. Captive zeros. Captives means that they're sandwiched, like 101. Obviously, the 1 and the 1 are significant because they're non-zero. But this 0 is significant because it's captive. So this would have 3 sig figs. Trailing zeros, but be careful because sometimes trailing zeros are significant and sometimes they're not. If you look down here, trailing zeros are significant when they are to the right of the decimal place. For example, it can't just be to the right of a decimal place. If I said 0.01, you would go, ooh, that's to the right of a decimal. That's important. But no, that would fall down here. This is a leading zero. It's in front of this number 1. It is not important. However, if I had 0.010, it's to the right of a decimal point, and let's add that in there, and a number, then it's important. 0.010 would have 2 significant figures. This is a leading zero. Leading zeros are not significant. And obviously I'm not going to have a leading zero. If I wrote a whole number like 101, I'm not going to write 0101. That's silly. No. Leading zeros means it can be after the decimal point, but it's before the number, and then any number, any zero that's after a number after that decimal is important. In scientific notation, let's say that I have a scientific notation number where I said 1.00 times 10 to the third power. Any digit in scientific notation is significant, so this would have 3 significant figures. Let's do some examples. Here's some. This number 3090. Obviously the 3 is significant and the 9 is significant. This 0 is captive, it's sandwiched, so yes it is. This is a trailing 0. No, it is not significant. This would only have 3 sig figs to it. This number, this decimal point, obviously this 8 is and this 2 is. These zeros are leading zeros, right? So we do not count them as significant. This 0 right here is sandwiched, so yes, we count it. This is trailing. It is after the decimal and after a number. Yes, we count it. So this number would have 4 significant figures. And if I asked you to write me this number in scientific notation, we would say 8.020, 4 significant figures, times 10 to the negative 123, and that would get us back to where we started. So let's talk about rounding significant figures. All numbers from a measurement are significant. However, we often generate non-significant digits when we do calculations, so sometimes we have to round. If the first non-significant digit is less than 5, we drop all of them. If the first non-significant digit is greater than 5, we increase it. If a calculation has several multiplication or division operations, wait until the last thing that you're doing to figure out how to round. For example, let's say I just did some calculations and my answer comes out as 15.73849, and I only can have 3 significant figures. Here's what I would do. I count 1, 2, 3, and I draw a line. And then I ask myself, does this 3 do anything to that 7? No, it's not going to round it up. It's got to be 5 or greater, just rounding rules. So I would write my answer as 15.7. Let's say I do a whole bunch of calculations and I get 18.750019. And I can only have 3 significant figures. So I'm going to go, okay, 1, 2, 3. I'm going to draw a line. Does that 5 do anything to the 7? Sure, it rounds it up. So I would write my answer as 18.8. Now what if I have 183 milliliters and I want to round it to 2 significant figures? So 183, rounded to 2. So if I went 1, 2, okay, is that 3 going to do anything to that 8? Nope. Can I just leave it as 18? No, because 183 versus 18 is very different. I would just put a placeholder 0 because this trailing 0 is not significant. This is still a 2 significant figure answer. We would record it as 180 milliliters. Similarly, if I said 48,457 grams and I want to go to 2 sig figs, I would say, okay, 1, 2. Will my 4 do anything to that 8? No. So I'm just going to say 48. But again, 48,000 is nowhere near 48. I'm just going to put 3 zeros as placeholders instead of those guys. 48,000 grams would be how I would write that answer. So let's look at some more examples. We want to round to 3 significant figures. If I've got a big number here, why don't you try covering up and seeing how you would round to 3 sig figs. See if you get that answer. Try the second, third, and fourth one, cover it up, and see if you get the following answers. Let's look at this. Stopwatch A is calibrated to 0 seconds. Stopwatch B is to the tenths of a second. Stopwatch C is to the hundredths of a second. So stopwatch A says 35 seconds. That's 2 significant figures. Stopwatch B says 35.1. That's 3 significant figures. And C says 35.08. That is 4 significant figures with each of those different timers. Here's some significant digit and placeholders information. If a number is less than 1, a placeholder 0 is never significant. Therefore, let's say I have 0.5 centimeters, 0.05 centimeters, 0.005 centimeters. They all have 1 significant figure. None of those leading zeros count. If a number is greater than 1, a placeholder 0 is usually not significant, like 50, 500, 5,000 centimeters. Only these 5s are significant. All these trailing zeros are not. The only time it would be is if it was written like this, 50 point centimeters. That would be telling me that this 0 is important. Or 500 point centimeters. That's the only time. So why don't you pause your video here and tell me how many significant digits are in the following measurements. And check your answers. How many significant figures in each of these? Now let's try rounding these numbers to 3 significant digits. And check your answers. All right, let's get to some more rules. If we are adding and subtracting, let's say I'm adding 114.3 plus 0.75 plus 0.581. Add them all up as you normally would. On your calculator, in your head, whatever. You line them all up. But your answer is limited by the value with the most uncertainty. And the most uncertainty means what digit did they all have in common? Did they all have to the 3rd decimal point in common? No. Did they all have to the 2nd decimal point in common? No. But they all have to the tenths in common. So I need to stop at the tenths and then ask myself, will that 3 do anything to that 6? Nope. So my correct answer, after adding a whole bunch of different numbers, and I'm looking at significant figures, I have to ask myself, what do they have in common? And stop there. So they all have the tenths in common. That's where I would end at significant figures. Why don't you try adding or subtracting these and round off your answer to the correct place? And check your answer. Now what about if I'm multiplying and dividing? If I'm multiplying or dividing, we don't look at the placeholders. We look at the number of significant figures. And then our answer is limited by which value has the fewest significant figures. So let's say I'm going to multiply 7.28 by 4.6. I ask myself, well, this number has 3 sig figs. This number has 2 sig figs. So I'm going to do the multiplication in my calculator and get a big old long answer. But I am limited to only have 2 sig figs for my answer. So 33.488, I'm going to go 1, 2. Will that 4 do anything to that 3? Nope. It's going to leave me with 33 centimeters squared. Why don't you try these and check your answers? I'm going to tell you to be careful with significant figures and calculators, because let's say I plug into my calculator 4.2500 plus 1.75, and I plug it in, and you're going to get 6. Except for your calculator is just going to tell you 6. But we need to look at, remember, when we're adding or subtracting, what placeholder did they have in common? And in this case, they have the hundredths in common. That's where I need to report my answer to. So this would be 6.00, whatever your unit is, centimeters, meters, grams, whatever it is. And in this case, if your calculator, if you write 36 times 73, you're going to get this big fat answer, and it's going to be easy to write down what your calculator says. But notice this has 2 sig figs, that has 2 sig figs. So you need to finish with 2 sig figs. If you have 2, 6, 2, 8, you need to go 1, 2. Is that 2 going to do anything to that 6? Nope. So 2, 6, 0, 0. You can't just write down what your calculator says. You need to go, okay, if I'm multiplying or dividing, I'm limited by how many significant figures I started with. And this is our last piece before I have some joining questions for you to do on your own. The percent concept. Percent expresses the amount of a single quantity compared to the entire sample. So it's a ratio of parts per 100 parts. Let's say I had a whole pizza. Whole pizza, there was 4 pieces on the pizza. I ate one of the pieces of pizza. So a single quantity that I ate was 1. The whole pizza had 4. So I would do my quantity divided by the total sample and times it by 100, and we know that would be 25%. We also know I could write 25% as 25 divided by 100. That would be 25%, right? So percentages can be written as parts of 100. So 10% we could write as 10 over 100. We can use percent expressed as a ratio as a unit factor. For example, let's say that the Earth and the Moon have a similar composition. Each contain 4.70% iron. What is the mass of iron in a lunar sample that weighs 92 grams? So I want to know the mass of iron. I want to know that piece. And I know that the whole piece weighs 92 grams. And I know that I'm going to multiply it by 100, and I'm going to get 4.70%. Can we work backwards from that and find the mass of the iron, the piece of the whole? Why don't you try that and tell me what you get? Let's see how you did. To get my, let's call this x, I needed to divide both sides by 100, so that got me 0.047 on the right. Then I'm left with x over 92 is equal to 0.047. And then I also know if I multiply across, I would get that x is equal to 0.047 times 92. And that would give me 4.324. Now this was all multiplying and dividing. So we need to look at, well, how many significant figures can I be significant to? This is 2, this is 3, so I'm limited to 2 significant figures. I should end up with just 4.3 grams of iron. You can always double check your answer as well. Do 4.3 divided by 92 and times it by 100. We should get 4.7%. Let's try this one. Bronze is an alloy of copper and tin. If a sample of bronze contains this much copper and this much tin, what is the percent copper in the bronze? Okay, so I want to know the copper. We'll call copper X. And I know that my whole sample is going to be 79.2 plus 10.8. Remember, it's part over whole. We're going to times that by 100. And this is my whole sample. So 79.2 divided by the total sample should give me 88.0%. We have 3 sig figs and 3 sig figs, so we wanted to end with 3 sig figs. Now I have 8 join-in questions for you. So as I go, I'm going to have you pause, figure out the answer, and then check them for each one of these. So you're going to do a lot of pausing. All right, that finishes up chapter 1 and the whole Let's Review section.